Alright, so we've learned how to draw scatter plots, we've learned how to analyse them in terms of direction, form and strength, and we've sort of started looking at putting lines on them or whether they're linear or not, but we haven't really yet spent time looking exactly how to put a line on, how to find the best line and all those different sorts of things. So we're going to start doing that now. So the first thing we want to talk about is a least squares regression line, and part of that we're going to talk about residuals as well. So a least squares regression line, or an LSR, so that's this LSR here, it's basically trying to be the best possible line for the data. So we would call that a line of best fit, and that'll come up a lot of times in a lot of different areas of maths. For example, that's a random scatter plot, and I want to say that's the line of best fit. So that's our least squares regression line. And we've got technical ways to find that. So it's the technical way to find that is actually all the distances from these dots to the actual line. When we shift the line and we find out when all of these distances added up together, and then when we square them, we square them and then we add them all up together, and whenever that amount is the smallest. So it's a tough concept, and we don't really have to understand it anyway, so I'll just quickly tell you. For instance, if I had a line here instead of where the blue one is, then the distances would be a lot greater, and then therefore when we squared them they'd be a lot bigger as well, and the total distance of all the dots would be a lot further away from this line than this line. So we're trying to find the line that is the closest on average to a piece of data, or all of the pieces of data. So here's the technical definition, but we're going to spend a bit of time clearing up these things that I've highlighted. The least squares regression line is the line that minimises the sum of the squares of the residuals. So we're probably starting to wonder what's a residual. Let me kind of clear that up as well. So the word residual or residue actually means like leftover or extra or excess. That we're just going over this section here now. So if I'm cleaning my shower and I find a bit of residue or something, they often talk about that in terms of like cleaning off things, cleaning residue. It's like the leftover bit that I haven't got to when I clean. That's the best example I can think of residue, but something that's left over. So residuals or residuals in a scatter plot are the leftover bit, or the amount of distance between our pieces of data and the actual line. So the distance from this dot down to this line, like directly down, that's the residual there. Or the distance from this dot all the way down to this line, that's the residual. Or the distance from this dot all the way up to this line, that's the residual. Or the distance from here to here, that's the residual. So every single dot, unless it's exactly on the line, is going to have some sort of residual value, or the leftover or the extra bit between the line and where the data actually is. So this line is like our approximation of the pattern, and these are the exact pieces of data that we got. So technical definition, our residual value, or the amount that's between the two things, is our data value minus whatever our predicted value is. So let's go over a few examples of that. I think that's the best way. So let's take this piece of data here. So we're looking for this amount of space here, and that'll be our residual value. So I want to say that, I might just make some space here on the next page, that our actual data value is 20, so you can see it's all the way up in line with the 20 just here, and our predicted value, if we predicted where that dot should be, is 10. So I'm just going to write that on the next page quickly. EGA, our actual data is at 20, and I'll just quickly bring that back over again. Our actual data is at 20, and our predicted data is at 10. Predicted data at 10. So we can see really easily the difference between that is 10, like 20 minus 10. But let's put it into our formula anyway. Residual value equals our data value minus predicted value. Now that should all fit on one line. I've just happened to put it on two lines both times because I ran out of space. So our residual is our actual data value 20 minus our predicted value 10. So our residual is 10. So going back to the actual graph, that means this distance here is 10. So our residual is 10, the leftover amount is 10. And it makes sense that it's a positive number because the actual amount of data is, we've got 10 over what we predicted, 10 above what we predicted. So we predict this one here to be positive as well, because we're going over. Might even do that one in a different colour. So this data was predicted, sorry, the actual data was 30, and the predicted amount, I reckon if we did like a dotted line across here, it's probably about 18. So there's our actual is 30, and our predicted is about 18. So let me put that one in. Actual data at 30, predicted at 18. So our residual, and using the formula that we had, is 30 actual data minus our predicted value 18. So our residual, our leftover amount, is 12. So the distance between this dot and this dot is 12. Let's do one final one together. I might do that in green. So again, it makes sense it's a positive number. You would expect that the distance from this predicted line to this actual value will be negative because it's underneath the line. So how much does it fall short of the line rather than being in excess of the line? So we're expecting a negative amount. Let's just quickly check. Our predicted value, just going across, it's probably about 35, let's say, and our actual data is probably around about 10. So we'll say E, G, C. Just do that. Might shift that one up for us. Our actual data was at 10, and our predicted was at, predicted data was at 35 there. So the residual is going to equal the data value 10 minus the predicted 35. So not 35 minus 10, but 10 minus 35, and that'll get us negative 25. So the residual, the leftover amount, is going to be negative 25 for this bit here. Now obviously the actual distance is 25, you can't have a negative distance, but we would say because it's under the line, we're now in a negative value. We've got, like we've fallen short of it rather than exceeding it. So you could do that with every single one of these, and this least squares regression line will be the point when we squared all these numbers, so 10 times 10, 12 times 12, negative 25 times negative 25. When we squared all of them and then we added them all up, our least squares regression line will be the line that meant that that was the smallest total value. So here, if we just had our three pieces of data, 100 plus 144, so it might be about 500-ish. If I moved it up here, the sum of the squares of our residuals might be like 1,000. So that's creating a higher number, it's a worse line. So we're looking for the line of best fit. If you're seriously not sure what I'm talking about still, don't worry, you can ask me in class, we can go over a few more. But the main thing to understand is the residual is the excess amount, and the least squares regression line is the line of best fit, and the calculator will do it for us anyway.